If we're going to be talking about sustainability, which is the whole purpose of this series of videos, then we need to start with the climate. It's a key to understanding where I'm actually standing to better know where I'm going to. I will give as an example my own climate. I live and work in Belgium, just off Brussels. And my climate, which is known for being bad, is actually not that bad. People complain about it, but it's not that terrible. To give you a better sense, it's actually called temperate, wet and temperate, which is why people usually associate that with bad. By the end of this video, the idea is for you to better understand how to analyze a climate, how this can be of great benefit when doing sustainable design, and why in this particular climate, buildings tend to be compact, several stories high, and tend to minimize heat loss to the environment. So with that being said, let's just start with the methodology, right after the intro, of course. For this climate analysis, we'll be using a TMY. TMY stands for Typical Meteorological Year. It's a standard climate file, which is the data for a constructed year. It's an average over a certain period of time. This data has been collected in a neighborhood in Brussels called Uccle, very close to the center of town, and I've taken it using Meteonorm. I will link all this on the description below. We will start by first looking at the dry bulb air temperature, which we will be using to subdivide the whole year into 3 climatic periods. Once we have that subdivision in place, we will then move on to discuss solar radiation, cloud cover, and daylight levels, or lux. I won't dive too deep, or at all actually, into wind, humidity, or rainfall, because as important as these parameters are, I'd rather just leave them out for this analysis and focus on the ones I mentioned just now, for the sake of time and given the relevance on the climate. I will come back to some of these parameters and do dedicated videos, but just to touch on them a bit, we have to understand that wind speeds are quite high throughout the year, and this could be uncomfortable for outdoor spaces. Then humidity is high, but not a problem on its own. And then if you know anything about Belgium, is that it rains a hell of a lot. It's just spread out throughout the year. For the dry bulb air temperature, I chose this particular graph because I feel it better transmits what the climate is like. You can see in the y-axis the temperature in degrees Celsius, and in the x-axis you will see the frequency for each of those temperatures. And this gives these kind of figures throughout the year, which when we start looking into more detail, we can see that in the months from November to March, temperatures are quite similar. We can group these months into a cool period, since the bulk of their temperatures oscillate between -2 to 8 degrees Celsius. Then in the 2 months right after the cool period and the 2 months before it, we can see a jump on the bulk of the temperatures. And now temperatures tend to oscillate between 8 and 18 degrees Celsius. This period with those temperatures we will call the mild period. And then we can see yet another jump where the bulk of the temperatures now oscillate between 12 and 22 degrees. This is not that warm, but let's call this, for lack of a better word, the warm period. Look closely at the shapes and you'll notice how these start to become more elongated as we move from the cool period to the warm period, implying that there's a higher amplitude as the months become warmer. Now let's turn our attention to solar radiation. And for that, let's look at this graph, which shows the average monthly cumulative values throughout the year, broken into 2 components. The direct, which is the one going above the zero, and the diffuse, which are the values below our zero. These values are in kilowatt hours per square meter. When you look at this graph, it's important to understand 2 things which are related. One, solar radiation is higher the more perpendicular the source of the radiation is to a certain surface. 2, these values are taken on a horizontal surface. This is crucial to understand because although it's true that solar radiation is weaker in the cool period than during the warm period, the way that this solar radiation is being measured makes us think that it's even more so than it actually is. Let me explain myself. I know it's a bit complicated. So I made a solar die this is what I call them, for each of the three periods that we just identified: the cool, the mild, and the warm period. For each die, I simulated the radiation falling on each facade. These are cumulative values throughout the period. So understand that there's 5 months for the cool period and only 3 months for the warm period. That has to be taken into account because there's more time for the cool period than for the warm period. You then see that for unobstructed southern facade, you would actually get a lot more solar radiation during the cool period than during the cold, warm period. So that's important to understand, because of course we want solar radiation in our facades during the cool period, and we don't want this on the warm period when it's already hot. We don't need additional external gains. This is an interesting finding on its own, and it partially explains why architects tend to focus our attention into having our buildings exposed to the south so that we can benefit of this phenomenon. Now let's move on to cloud cover. For this climate, the sky is predominantly overcast. We certainly did not need to do a climate analysis to know that, but I'm sad to say it is the case. 66% of the time, or 2/3, the sky is overcast. And I even have a chart to show it. Here in the y-axis, you can see time as a percentage, and on the x-axis, you can see the average hourly monthly values for each month. Something we can see when looking at this graph is that as we move from the cool period to the warm period, we can see that cloud cover at night tends to start to disappear, or at least drops or diminishes, whatever you call it. That hints at the possibility of using nighttime ventilation as a cooling strategy. It's more or less like having a blanket being removed at the middle of the night to allow for temperatures to drop. We actually have our warmest days when that cloud cover remains after a hot day, because the Earth is just not given a chance to radiate that heat out because that cloud cover remains. Now, the biggest impact of this cloud cover is what we're gonna see next. Let's talk about daylight, which is a fascinating topic. So much so that I make another dedicated video for this topic on its own. But for now, let's just cover the basics and refer to what we just discussed: cloud cover and the fact that this climate is predominantly overcast. When analyzing daylight, this is actually, I want to say good news, but it's not entirely good news. It's good because it's easy in a way. Why? Well, you'll understand in just a second. It mainly has to do with the fact that an overcast sky is one that is completely different from a bright, clear sky. To illustrate this, I took 2 videos. One on a cloudy day and one on a sunny day. I took them both from the football pitch where my kids go to play football with a lens that I particularly like. So let's first look at the cloudy one. And you can see here that the sky is brightest at the summit, or the zenith as it is actually called, the point right above where the camera is. And then it becomes gradually darker as we approach the horizon, and the daylight is fairly even distributed. Now compare that to the clear sky, where you can see that the brightest spot is of course the sun, then the darkest one is the point directly opposite the sun, and then it becomes brighter and brighter as we approach the horizon. So as I said, they're just vastly different. So what does this mean for architecture and simulations and understanding our daylight environment? Well, it means that we can get away with simulating with the static model, which is the one based on something we call daylight factor, which really stands for the percentage of light that comes into a space in relation to the light that is outside. But for this, we need to focus only on the diffuse component of daylight. This is a graph representing the diffuse average hourly values for each month. Now, understand that we need at least 5 kilolux in the environment in order to provide adequate lighting inside. If this is the benchmark, then in December, January, we're going to achieve this about 5, maybe 6 hours a day, which I understand is a grim conclusion, but it is what it is. We should probably not strive to have our spaces be naturally daylit on these 2 months of the year, because the potential is just not there. And that takes us into our conclusions. This is a predominantly cool climate with a 5-month-long winter or cool period. The emphasis should be placed into keeping that heat inside. We do this by designing compact buildings with high-performing envelopes so that they keep the warmth inside and slow that heat exchange to the environment through proper insulation, of course, and by keeping our openings at check. Now, the past few years, decades, window performance has been increasing, but still this should be taken into consideration. And that brings us to yet another challenge, which is how do we properly illuminate our spaces, given that we have to keep our window sizes relatively low and that the environment does not provide that much illuminance altogether. Now, the environment does provide a lot of illuminance throughout the year. It's just 2 months a year that we should probably not consider into our simulations. And again, sustainable design does not stand for bad design. We can still have beautiful big windows. We just have to understand the consequences of that. That's all. And then finally, given the lower cloud cover at night during the warm period, we should not neglect the opportunity for optimizing nighttime ventilation strategy. We should design our windows and openings in a way that they can be opened at night, considering the impact that this may have in user comfort in terms of how much noise will be coming in from a particular window and that kind of thing. We should also couple this with materials which have higher thermal mass, such as brick, concrete, stone, so on. If you made it this far, sincerely, you have my thanks. I hope I managed to tap into your interest, to convey to you why we analyze the climate and how this impacts architecture when doing sustainable design. Well, that's all for me today, so hope to see you again in the next one. Bye. Vamos a empezar, Qué apretado el reloj. Si el reloj está apretado, el video es una cagada, así que mejor ahí. Se iba confiado el ninjera en la playa.